Hello everyone. So this is a question from JEE Advanced 2025 paper 2. For the reaction sequence given below, the correct statements is R. So we have a starting compound here. So this guy is treated with LiAlH4 to get P, then Q, then R and S, and few options are given to us. So based on P, Q, R and S, so we have to obviously find out P, Q, R and S. Only then we can think about these options. The chapters involved is alcohols, phenols and ethers and hydrocarbons. Okay. So to start with, let us concentrate on our starting compound. So the starting compound is pH, is basically a benzene ring, CH2, and it is connected to, one second, so it is taking up some space. Okay, so there is a benzene ring, CH2, this bond is there, and C double bond O. Yes, so I would want you to focus in this part of the molecule because this is where things are going to happen. Okay, so I will yeah, this part of the molecule is important. This is our starting compound. Okay, so just looking at this part of the molecule of the starting compound, so I will draw this part separately. So yeah, C double bond O. Yes, so these guys are known as delta valerolactone or delta lactone or lactones in general. Okay, so specifically its name is delta valerolactone, or it is also known as delta lactone, or it is in general known as lactones. Okay, so these are cyclic carboxylic esters, very important. Cyclic carboxylic esters. So lactones are nothing but they are cyclic carboxylic esters. So you can see there is a R, that is a C double bond O and R group, or a C group, right? So these guys, that is lactones, they are derived from the corresponding hydroxy carboxylic acid, very important. So these guys are derived from the corresponding hydroxy carboxylic acids. So what are hydroxy carboxylic acids? Those carboxylic acids which contain OH and COOH group on the same molecule. Okay, so these lactones, they are derived from the corresponding hydroxy carboxylic acids by intramolecular esterification, by a process called intramolecular esterification, right? So this is some information about lactones. So for example, if you have this guy OH, and can you see this is an example of a hydroxy carboxylic acid, right? So whenever we do esterification to this guy, that is H plus and heat, and this is a reversible reaction, we get the after intramolecular esterification, we get the respective lactone. So let us see the number of carbon atoms here: 1 2 3 4 5. So we will get something like this: 1 2 3 4 5, right? So this is this is the lactone that we started with. This is which is present in our starting compound. Okay, and also the solid wedge which is present in our starting compound, it represents a bond or a valency which is above the plane of the paper, right? This is a single covalent bond, but this is not on the plane, this is above the plane of the paper. Okay, so the first thing that we treat our starting compound is with LiAlH4, which is lithium aluminum hydride, and it's a reducing agent, right? So, and also this is a cyclic ester, right? So let us try to understand how normal esters will react with LiAlH4. Okay, First, let's try to understand how will normal esters react with LiAlH4. Okay, we'll talk about cyclic esters after a bit. Let's first understand how normal esters will react with LiAlH4. So if we have a normal ester, for example RC double bond OR dash, and we treat this with LiAlH4, so this bond breaks and we get two different alcohols. One is RCH2OH and the other one is R-OH, right? So the reduction of normal esters give a mixture of two alcohols, one from the acyl group, this is known as the acyl group, so this contributes to this alcohol, and other from the alkoxy group, this is known as the alkoxy group, this will give us this alcohol. Okay, so we have understood how normal esters behave in the presence of LiAlH4. Let's talk about how abnormal esters, or the cyclic ones, behave with the LiAlH4. Okay, so the good thing is that the cyclic ones also behave in a similar way when they are treated with LiAlH4. So our starting compound is this guy. So we have pH and C double bond O. Yeah. So let us give numbers to them: 1, 2, 3, 4, and 5. Okay. So the bond breaks here. The way it broke here, right? Same thing happened here also. The CO upon the action of LiAlH4. So we will get, obviously, this part will give us one alcohol and this part will give us another alcohol. So we will have two OH groups. Okay, so we will get pH C is there, it is linked to one C, it is linked to one more C, which will be converted to an alcohol. Similarly, it is linked to one C, which is linked to one more C, it will be converted into alcohol, right? And giving them numbers 1, 2, 3, 4, 5. So you can see what happened. This third carbon has now an alcohol group attached to it. This fifth carbon has now an alcohol group attached to it, right? So this is what is our P. This is our P, okay? And then to find S, we treat P with H2SO4 and 443 Kelvin. Okay, so can you see P consists of OH groups, and we know that when alcohols are heated with concentrated H2SO4 at 443 Kelvin, they undergo intramolecular dehydration to form alkenes. So I will write this point: when alcohols heated with concentrated H2SO4 at 443 Kelvin, they undergo intramolecular dehydration to result into alkenes. Okay, so therefore P, so our P is, so let's draw our P again, pH C and CH, it is connected to CH2, CH2OH, CH2, CH2OH. So we are treating this guy with H2SO4, which will contribute a lot of H plus, okay, at 443 Kelvin, since it is an acid. So what will happen? O has lone pairs, so this lone pairs will be given to this H plus. Similarly, there will be other H plus also. This OH will also behave in a similar way. So that's why because of the donation of lone pairs to this H plus by both the OH group, P will ultimately become pH C CH CH2 CH2 OH2 plus and CH2 CH2 OH2 plus, right? Now can you see this oxygen has a positive charge, but it's a highly electronegative element, so therefore it's kind of unstable. So therefore what will happen, this molecule will easily lose water molecules. So this O can take away these electron pairs, this O can also take away these electron pairs, resulting into carbocations. There will be positive charge in these carbons. Okay, so therefore this guy ultimately, after loss of water, minus H2O will become two molecules of H2O. So it will ultimately become pH C, you have CH, CH2, CH2 plus, and CH2, CH2 plus. Okay, and the next step will be, after the carbocation has formed, the next step will be elimination of a proton to form alkene. Okay, so what will happen, I can write this CH2 in this fashion, one H separate. I can write this CH2 in this fashion, one H separate. So what will happen, these sigma bonds will become pi bond, and H will go out in the form of H plus. These sigma bond will become pi bond, and this H will go out in the form of H plus. So therefore ultimately we will get alkene. So this is how dehydration of alcohol takes place. So let's say minus 2H plus going out, so we will be getting pH C with a bond with CH, and CH double bond CH2, CH double bond CH2. So this is one of the this is S, but one more kind of product is possible, because rearrangements is also possible. Okay, so this is S, correct, but this is not the only S. Okay, because rearrangement is also possible. Can you see here, we have a primary carbocation, so there can be a hydride shift from here to this, which will result in a secondary carbocation, right? So I will show that shift. So I will draw the previously obtained carbocation again. So the previously obtained carbocation was PHC CH CH2 CH2 plus CH2 CH2 plus. So this is what we obtain, isn't it? Yeah, this is what we obtained originally, right? So now taking into account of the rearrangements that is possible, so I will write this CH2 in this fashion, one H separate. So now what can happen, this positive charge will shift here, this hydrogen can shift here, so it will result into this carbocation. So we will get pH C CH CH positive charge CH3 and CH2 CH2 plus. So due to the rearrangement we get another carbocation, and then again elimination of proton to form alkene. So what will happen, I can write again the H out, and what will happen, this will become the pi bond and H plus goes out, this will become the pi bond and then H plus goes out. So we will get one more alkene. So I will use arrow to show. So we will get one more alkene which is possible, that is PH C double bond CH CH3 CH double bond CH3 CH2. Yeah, so this is also S. Okay, so this is one S, this is also S. Multiple products are possible due to rearrangement. Okay, cool. So we found what is P, we found what is S. Now next let's talk about Q. Okay, so to find Q we have to start with P. Okay, P is again PH C, this bond CH2 CH2 OH CH2 CH2 OH, right? So we are treating P with CrO3 and H2SO4. So this is known as our Jones reagent. Okay, this is known as the Jones reagent. and the job of this guy is to convert 1 degree alcohols to carboxylic acid. This is the job. Okay, so what will happen? Obviously this group will become COOH, this group will become COOH. So therefore Q will be when we treat P with Jones reagent, we'll get pH C CH2 COOH and CH2 COOH. This is our Q. And then to find R, so we treat Q with NaOH and CaO, and also we have heat. So whenever we have carboxylic acid, whenever we heat carboxylic acid with soda lime, so mixture of NaOH and CaO is known as soda lime, a molecule of CO2 is lost and an alkane with one carbon atom less than the carboxylic acid is formed, which is basically decarboxylation. So I will write that down. When carboxylic acid heated with soda lime, a molecule of CO2 is lost and an alkene with one carbon atom less than the starting carboxylic acid is formed, which is our decarboxylation reaction. Okay, so here we have our Q. Q is pH C CH2 COOH. There is obviously a H here. Sometimes I may not write it. Okay, CH2 COOH plus NaOH. So what will happen? Very easy. The carboxylic acid, whenever they are treated with NaOH, they will form the sodium salt of the carboxylic acid. So we will get pH C CH CH2 COONA CH2 COONA, right? And then we treat this with a combo of NaOH. Obviously calcium oxide is also there. So what is going to happen? This Na, so look very carefully, this Na, this O and this CO2 will come out in the form of Na2CO3. Okay, so I will underline them. Na and Na is Na2, CO2 and one O is CO3. So this comes out in the form of Na2CO3. Okay, there is one more mole. So assuming there is plenty of NaOH, so Na and Na from here and CO2 and O from here. So again 2 moles of Na2CO3 out. And what will happen? This H becomes a part of your CH2. This one more H becomes a part of your CH2. So ultimately our R will be pH C CH CH3 and CH3. So this will be our R. Okay, so this is after decarboxylation. So we have got P, Q, R and S, so we know them. So therefore let's talk, and so now we can look into the options. Okay, so A, what is A saying? P is optically active. Okay, so let us look at C. Let us look at P. P is pH CH2 CH CH2 CH2 OH CH2 CH2 OH, right? So for a compound to be optically active, there should be minimum 1 chiral carbon in the molecule. Okay, in this compound there is no chiral carbon. For example, let us look at this carbon. It is attached to this group CH2CH2OH, which is similar to CH2CH2OH. For example, let us look at this carbon. It has 2 similar hydrogens. Let us look at this carbon, two similar hydrogens, and also pH is planar and also consists of double bonds. So therefore, there is no chiral carbon in this molecule. Okay, so therefore P is optically inactive. Okay, so therefore A is incorrect. A is incorrect. Then let's look at option B. So option B is saying S gives Bayer's test. Okay, so remember S were alkenes. So we obtained, there were multiple products. So this was, one of the S, this is the other S. Okay, so we have to know what is Bayer's test. Okay, so Bayer's test is, alkenes, they are readily oxidized by cold, dilute, neutral or alkaline KMnO4. Okay, so alkenes, whenever they react with dilute, it can be neutral or alkaline, cold. Be careful, cold, dilute KMnO4 solution. So whenever alkenes react with them, we get vicinal or 1,2 diols. So we get vicinal, or they are also known as 1,2 diols. Basically they are converted into OH groups adjacent to each other. Okay, and this KMnO4 itself gets reduced to MnO2. So we get one more product, that is MnO2, right? During this reaction, the typical pink color of KMnO4 solution is discharged and a brown PPT of MnO2 is formed. So that's why this test is also used, to check saturation or unsaturation. Okay, for example, I will give you an example. If you have an alkene, let's say CH3 CH double bond CH3. So whenever you treat this with KMnO4, and let's say you have taken neutral, so therefore water, so what will happen, we will get a diol. So this CH, one OH will be attached, this CH also one OH will be attached, and this double bond will be converted into a single bond. So we will get CH3 CHOH single bond CHOH CH3, and as usual KMnO4 will be converted into the brown PPT MnO2 and we'll get KOH. So this falls under the category of Bayer's test, right? And so the option is saying S gives Bayer's test. Now if we look at S, it is an alkene, it consists of double bonds, right? And the other S also consists of double bonds. So therefore both of them are alkenes, so therefore S will give Bayer's test, so therefore B is true. Okay, so B is a true statement. Okay, then let's look at C, option C. Q gives effervescence with aqueous NaHCO3. Okay, so let us look at Q. What is Q? pH, CH2, CH connected to CH2, COOH, CH2, COOH, right? So you can see there are carboxyl groups. Okay, whenever carboxylic acids, whenever they are treated with sodium hydrogen carbonate, that is carboxylic acid plus NaHCO3, okay, this carboxylic acid gives effervescence or bubbles due to the evolution of CO2 gas. Okay, so we get the salt, sodium salt, respective sodium salt plus water plus CO2. So the effervescence is because of this CO2 gas. Okay, so in the question, in the option, Q is a carboxylic acid. Can you see? So therefore this, whenever it reacts with aqueous sodium hydrogen carbonate NaHCO3, therefore it will react with NaHCO3 to give effervescence or CO2. So therefore C is a correct statement. Okay, so C is true. And the last option is saying R is an alkyne. Okay, so we got what is R. Yeah, so this was, remember, this was our R. So this is not an alkyne. Okay, it is actually alkyl benzene, because this is a benzene ring to which a alkyl group is attached, right? So therefore this is an incorrect statement. So therefore D is an incorrect statement. So they're asking us correct statement. Okay, so P is optically inactive, so this is false. S gives Bayer's test, correct, because S is alkene. Q gives effervescence with aqueous NaHCO3, correct, because Q contains carboxyl groups. R is not an alkyne, it is a benzene ring with alkyl groups. Okay, thank you.